So let's look at a few examples on one functions of two random variables. So as we just discussed, if you have a region in the 2D plane, xy plane, the probability that the random variables x and y belong to that region is given by, we just saw it a few minutes back, the area under the joint density function, but the area evaluated only over the region of interest. So I'm going to make use of this concept in finding the density function of, let's say, one function of two random variables. So the classic examples are z equal to x plus y, let's say x minus y, x over y, x squared plus y squared, or it's a square root of x squared plus y squared, or the order statistics max of x comma y, min of x comma y, etc. So we'll try to do a few of these problems, and both x and y could be continuous or discrete, etc. Right? So let me start with the classic problem, z equal to x plus y. So remember what the problem is. So you have the joint density function is given, and you have the function given, and we want to find out the density function of z. Okay, this is the classic problem. So a couple of ways you can do this. These are very standard problems, but since it is new to you, the easiest way, which makes a lot of physical sense, is to start with the distribution function of z. So remember, by definition, z is, this distribution function is by definition probability of z less than or equal to z. Right? So of course, this is the unknown quantity. The whole idea is to somehow write this unknown quantity in terms of this known quantity. And then once you have the distribution function, we can take the derivative and find the density function. So it's not a good idea generally to try to solve this problem directly for this. This is, as you will see through several examples. But here is the problem. Z is given. Of course, we need to translate the unknown in terms of the known. So z is given to be x plus y. So we can write this as a probability of x plus y less than or equal to z, right? Because z is given to be, so this is where we are. So what we do next is, especially with the two random variables, it's a good idea to find out in the two-dimensional plane where is the region where this inequality is satisfied. Once you can find out the region, then we can use this concept. If I know the region, I'll integrate over that region. Remember, after all, I'm trying to find out the probability. So x plus y equal to z is what? It's a straight line. And how will it go? This way means this way. That's a sword fighting. Right? So it's so why is this? Because you put, to draw any region, you put one variable equal to 0. So if you put y equal to 0, so this is of course x, this is y equal to 0, this is z, right? And x equal to 0, this is z. And this is, of course, I consider z to be positive. If z is negative, anyway, it's a translation of this line, shift. So where is so one side is less than, one side is greater than. Which side is x plus y less than or equal to z? So you don't have to do guesswork. You put your point, you put say here. So if this point is 0, 0. So then if I put this inequality, so the 0 is less than or equal to c. So definitely on this side, right? Or if you put your hand here, you can see that's not the region, right? So one way or the other way, you can figure out that this is the region where this inequality is satisfied. Once you find that out, then we go back to, so we just need to integrate over the density function over that region. So you could take a strip like this. So the strip in general comes from minus infinity up to this point, then all such strips like this. So you could write this as double integral fxy. The way I have written, I decided to integrate on x first. X goes from minus infinity. What will be the limit on y? The limit on y is dictated by this line. So y is going to be z minus x.
Yes, z minus x.
Right. I'm sorry. The strip is x. Y is z minus x. Similarly, x is z minus y, right? We just want to find out up to what value of x it will come. I'm integrating on x, right? Not on y at this point. So x comes up to z minus y. And y, how about y? Looking at this diagram, when there are no restrictions, y goes from minus infinity to plus infinity. That will be y. So don't write here carelessly dx by or dy dx. If I write something, you should mean it. But again, why did, as I said, you could have taken, there was no reason to have taken a horizontal strip. I could have taken a vertical strip also. So the same thing, I should be able to write this as fxy. You don't have to do both, but I'm saying you could have. Here I am integrating on which variable? Y, clearly. Y goes from minus infinity to up to this point. So the value of y is here, z minus x. So y goes from minus infinity to z minus x. Now you immediately should write down this as dy here, right? And then x, of course, goes from minus infinity to plus infinity, right? That's dx. All right, so that's only FCC. So it was like this, right? So we need to integrate here, and we used a strip like this. So this is x plus y equal to z. As I said last time, we could this I will be using this again and again. I hope you derived it. So what was it? If you have a function gx which is ax bx, and then it's a derivative with respect to x. You remember derivative of the top limit, right? So remember here the derivative is with respect to y. So this is a derivative of the top limit with respect to x. Then in the variable of the integration you substitute the limit. So it will be x comma bx minus, do the same thing on the denominator, exactly the same thing. So the derivative of the denominator with respect to x. In the variable you substitute the lower limit. And the third term, which is what you would have done otherwise, just take the partial derivative of the inside quantity with respect to, now if this is not a function of x, this term would not be there, right? So let's apply that here. So I'll do, in this case I'll do it both, simply because it's the first problem. You just need to do it. Remember, these two are identical, right? You don't have to do both. So from here, the density function of z is given by, of course I should take the derivative of capital F with respect to z. Now when you have a, look at here, when you have limits which are constant, the derivative with respect to a constant is 0. So this term and this term is 0. So then the limits stay as it is, you take the derivative inside. So that will be the case with respect to the first integral, right? Because it is, these are constants, the derivative will come here. So this is, if you want, you can write one more line. This is d by dz of minus infinity to z minus y fxy x comma y dx, I guess. Right? We just need to do this inside one. So look here. Hello. So the derivative of the top limit, because the top limit is a function of z, that derivative is 1, right? And what's the variable of integration here? Remember, we are dealing with this integral. So you have to see, I of course wrote it for you clearly. The variable is integration. Otherwise, there are two places you could substitute. You should substitute wherever is the variable of integration. So that's going to be 1 multiplied by fxy z minus y comma y, right? Minus the derivative of the bottom limit. That's a constant, so no contribution. The third term is the derivative with respect to z of this quantity. This is only a function of x and y, so no contribution. So this is it. Simply the answer is this. Let's try here. So here also, from here also you get fzz is minus infinity to plus infinity. So the derivative with respect to z, this is 1, but this here the variable is y. So this is going to be fxy x comma z minus y, z minus x, right? Bottom limit is 0, third term is 0, so this is this. So that's in general, this is the answer. You can either use this formula or this formula. Now, in particular, if x and y are independent, then what happens to the joint density function? Anybody? Joint density function becomes what?
fxy of z minus y into fxy of y.
Joint density function becomes the product. Then FCC, you can write this as minus infinity to plus infinity fx of z minus y multiplied by fy dy. Or it's the same as minus infinity to plus infinity from here, fx of z minus x fy x dx. So what? But anybody can see this operation? If those of you know convolution, you can say this is the convolution of two density functions. Those of you who do not know convolution don't see anything, right? Convolution of what? Two functions here, fx of z and fy of z. So symbolically, same thing here, same two functions are convolved. You can write it in two different ways. That's what so if you integrate on x direction first, you can write it this way. If you integrate on y direction, you write the same result differently. So you can write this as symbolically if you want fx of z convolved with fy of z. Not fx of x, fx of z. See, like the time function. Fx of t and fy of t, if you convolve, this is the way you write. So this is some of you might have seen this form. If two random variables are independent and if you define z to be their sum, the density function of their sum is not the sum of the density functions, is the convolution of the two density functions. Now, after 1 hour you ask why convolution? That's bad. That's the proof is here. This is not always true. This is only true if they are independent. If they are not independent, you have to do this work. So there are a couple of special cases to this. What if the random, just to see about the limits, what if the limits, what if the random variables are non-negative? Say x is non-negative, y is non-negative. So of course FCC is still see, in this case the density function lives only here, right? The density function is 0 here, 0 here, 0 here. This is x, this is y, right? That's given to you. So where is this inequality? FCC is of course probability of z less than or equal to z. C is x plus y less than or equal to z. X plus y equal to z is this line. So where is the region x plus y less than or equal to z? So you only need to integrate within the triangle because there is nothing to integrate here, here, here. So how will you integrate it? So what will be the limits here? Anyone? You could take a horizontal strip, goes from 0 to z minus y, right? And vertical strip, not vertical strip, and on y, see it's not minus infinity to plus infinity, it depends on the problem, right? So here you just have to, right, only 0 to z, so you can see, why is this z? Because you put x equal to 0, you can see y is z, right? So let's say fxx is exponential and fyy is exponential. And x and y are independent. If x and y are independent, or let me, if you want, you can, before we substitute, let's take the derivative of this. So the derivative, look here, already there is a limit here. So I'll do this, you see whether it, so the derivative of the top limit, which is 1, then in this function, what is the variable of here? I'm sorry, the outside integral is with respect to which variable? Y. So it may be a good idea to write here. So you clearly know this is with respect to y, this is with respect. So you substitute the top limit for y. So here you substitute z. Here also you have to substitute z. So this becomes 0 to 0, no contribution, right? Because 1 multiplied by an integral which goes from 0 to 0. So we don't have to worry about this. We don't have to worry about this, that's a constant. So we only have to worry about the third term. You see that? You have missed it? You are looking something else? Look here again, you need to find the density derivative with respect to z of the distribution function. So we start with this because we use that formula. The top limit depends on z. So its derivative with respect to z is 1, right? That you can see. Then we look at there, then we need to substitute this limit into the variable of integration, which happens to be y. So you look around where y is, I see at 2 places. Both the places you substitute z. Once you substitute here, you don't have to worry about anything because this integral becomes 0 to 0. So there is no contribution. Bottom line is taking the derivative and doing all this, it didn't contribute to anything. So we proceed to the next term, which is minus the derivative of the bottom limit. That's a constant, again no contribution. So the third term only matters, that's you keep the limits as they are, that's with respect to y, and take the derivative of this quantity with respect to z. The derivative of the with respect to z is 1. Then of course I know I'm integrating with respect to, integration is with respect to x. So this goes to fxy z minus y. Derivative of the next term, bottom limit, it's a constant, so there is no contribution. Third term, derivative of this with respect to c, no contribution. So this is it. Very similar to that, except the limits are, all I wanted to show is that it's not. So when you have a non-negative case, you shouldn't be putting here 0 to minus infinity to plus infinity. How will you know what to do? Always do the problem given to you. And so let's complete this. Oh, in this case, so now you can, of course, if in this case, now you can substitute this data. In other words, it's given to you that x and y are independent, so I can write this as fx of z minus y multiplied by fyy, right, dy. All right, now if I substitute integral 0 to c, lambda e raised to minus z minus y, lambda e raised to minus y dy.
Lambda e raised to minus lambda x. Lambda into z minus y.
Fxx is lambda e raised to minus lambda x.
Lambda e raised to minus lambda into z minus y.
Yeah, where are you? Look at here. Fx evaluated at z minus y. Hello? Yeah? Look here, this is not x here because we have replaced it by z minus y. You don't see it?
So not that function lambda e raised to minus lambda into z.
Okay, very good. The variables are good? Yes, of course, right. Oh, look here, now if you expand, e raised to minus lambda z goes outside because the integration is with respect to y. So this becomes lambda e raised to minus lambda z, and then you have 0 to z, e raised to minus plus lambda y and minus lambda y, that's e raised to 0, 1. So what is it here? Simply dy, isn't it? So this integral is simply z. So the answer is lambda squared z e raised to minus lambda z. For z, if x and y are positive, of course their sum is positive also. So that's the answer. Okay. So this is lambda squared z e raised to minus lambda z for z positive and 0 otherwise. And let me quickly do one more. So this is, that's a gamma density function. So you have a small theorem here. If you have independent exponentials, if you add up, you get gamma, one particular form of gamma. So if you y, here is the proof. So remember, few minutes back we had another problem. What was it? fxy. Anybody has it? E raised to minus y or minus x? What is this? This was the joint density function. So we can try to find out x plus y. Again, it's best to do the given problem rather than try to substitute into any formula. So for example, here, where is the density function non-zero? In which region? Look here, it's already given to you. The density function is 0 everywhere else. So only in this region, y is positive, x is positive, but x is greater than y. So that would be where? Here or here? All right, so you should know these basic stuff. Right? So this is the region, and the line x plus y equal to z is here. So which region are you integrating? FCC. Probability of x plus y less than or equal to z. Where is the region where this inequality is satisfied? Anyone? Yeah, remember, it's to the left of this line, but the density function is 0 everywhere except here, right? So you integrate here. Which way should I take a strip? Anyone? Look at here. If I take a strip like this, what happens? This strip will go like this up to here, then the limits change. Horizontal is easier here. Both the ways you can take, but if you take a strip like this, so so that strip is, what are we integrating first? So I know it is x, then y. So what is the lower limit on x? Look at here. X goes from y to, right? So x goes from y to z minus y, and y goes from, you can see from here to here. What is this point? So this point, of course, this is x equal to y. So you put x equal to y, y is z by 2, right? So you see all these details, you just have to solve for each problem, right? There's nothing you can throw up as a canned formula all the time, right? All right, so if you take the derivative here, again we can sort of do mentally. Let's see. The derivative of this is half, right? Look here, half. But the variable is y, so wherever you see y, 3 places, you should put z by 2. So this becomes z by 2, this becomes z by 2, no contribution. Derivative of the bottom limit, so you will get used to it once you do few problems. A derivative of the bottom limit, again no contribution because it's a constant. So this will become integral 0 to z by 2 here. Derivative with respect to z, this is 1. This derivative, this variable of integration is x, so x is replaced by z minus y. So you will see right. So let's complete this problem. The density function is given to be 0 to z by 2. fxy is this. So I replace x by z minus y dy. So the answer is e raised to minus z integral 0 to z by 2, right? E raised to y dy. So this is e raised to minus z, e raised to y 0 to z by 2. What is it? Right? Z go, what is the, this is for z. What is the limit on z? Not minus infinity to plus infinity, greater than 0 and 0 otherwise. Even I don't know whether this answer is right. How will you check whether this answer is right? Why double integral? All right, so we can check this, see whether. So let's substitute. So easiest thing is just do it separately, right? E raised to minus z by 2. So what is it? E raised to minus 3z by 2 minus 3 by 2 minus so what happened? 0 to infinity. No, I didn't. Tell me what are the terms here? This multiplied by this is e raised to minus z by 2, isn't it? Minus integral 0 to infinity e raised to minus z dc, is it? Hello? This multiplied by this is e raised to minus z by 2. All right, so this is minus half, right? 0 to infinity minus e raised to minus z minus 1, 0 to infinity. So this is 2 minus 1 is 1, isn't it? We go, this flips up, top limit is 0, bottom limit is 1. So that's 1, that's 2, this is 1. So this is a density function and this is the right one. And if you want a problem, this is again a classic problem. So you can suppose what is this density function? Anybody? Right. So this is fyy. So this is the problem. X and y are uniform between 0 to 1. Z is x plus y. So the density function of z is x and y are independent also. Hello? We already learned the theorem. If x and y are independent, z is x plus y. The density function of z is fx convolved with fy. So you have to convolve this with this. If you know how to convolve two rectangles, what will you get?
A triangle.
Well, you just got lucky. But that's true. No, this is solved in detail in the class, I mean in the text. So I'm just not going to go through the details. So this will turn out to be z, and this is, I think, 2 minus z. So you should go and check whether you can actually convolve this with this, follow the steps and get the triangle. See, if x goes from 0 to 1, y goes from 0 to 1, the sum will go from 0 to 2, right? That's kindergarten, right? What is not kindergarten is the convolution, right? So again, so you know how to convolve, right? So it is FZC is, we just have fx of z minus y, fyy dy. So you have to take fxx, fxx is here, then flip it, so you get fx of minus y, that's what you want, fx of minus y. You have to go through the convolution steps, then you shift it by z so that you get a shifted version. This will be fx of z minus y. This should be multiplied by fyy. Fyy is like this, right? I just brought this term here. So how much are you shifting? I am shifting by z. So when you multiply this with this, you can see this region is, and that is the region you need to integrate. So this region need to be integrated from 0 to c. Since this is 1, this is 1, when you integrate 0 to c, you get 1 multiplied by z, which is a line. That will go up to, then the shape will change, etc. So you go through this. So the key, I'll summarize this by, we just did one example. If z equal to x plus y and x and y are independent, then the density function of the sum is the convolution of the two density functions. And if they are not independent, I gave you the formulas, right? It will be integral fx of z minus y multiplied by fy dy.